All right, welcome back, everybody. Welcome to this lightning talk session. Our first speaker is Masahito Hayashi. Go ahead.
Just a moment, sorry. I should. Okay. Can you hear me? So now I want to.
We don't see your slides anymore.
Okay. So now I want to talk our another result with Kunwa.
Masahito, we can't see your slides right now. Did you stop your share? I can't see.
Okay. Just a moment. I will do.
Please share your screen.
So this one and okay. So today I want to talk about our result for the permutation enhances classical communication assisted by entangled states. As you know, this is a picture for the super dense coding. In the super dense coding, we initially prepare one well state, and depending on two message to bit, we apply X and Z. Then we send quantum state by using a noiseless qubit channel. Then receiver apply bell state measurement. Then we can recover 2 qubits. So this is a super dense coding. So in that case, we can send 2 qubits by using one noiseless qubit channel when we can prepare a bell state. So this problem can be extended to the noisy channel case. In the noisy channel case, we assume that we can prepare any type of entangled state between the sender and receiver. And depending on our message, we can apply this operation. So then we can send information. This problem is called entangled assisted classical communication. And the maximum transmission rate, the capacity equal to the maximum mutual information for the noisy channel N. Here, there is no limitation for the pre-shared entangled state. Now we consider slightly different setting. In that setting, we also fix the pre-shared entangled state rho 1 to rho n. This is same. So, and also we restrict our operation for the coding. So in that case, how obtain our transmission rate? Of course, this is depends on the situation. So then we obtain this result. There is we consider two kinds of class. First class is we allow local operation and global permutation across n input system. So here is the n input system. Here is the n entangled state, and we have a local operation. And in our coding, we allow permutation across this n input system. So this is our coding operation. In that case, the capacity is singularized mutual information between the this EB and X is somehow operation for the local operation on the single system, and B is output system for this one. So using this one is this one. And also, if we allow only local operation and one-way classical communication for this N input system, so classical communication across this N input system. So then in that case, we have a mutual information between X and X, this one. So in that case, this mutual information is strictly smaller than this mutual information. And also both operations preserve the set of several states on this input system. So this operation does not produce any entangled state. In some sense, that kind of preserving the several operation is not so useful for some entangled resource theory, but our result mentions that this kind of local operation enhances the performance of entangled state for transmission of classical information. This is counterintuitive. So this is a main result of our paper. Thank you very much.
Thank you very much, Masahito. So if you have questions, of course, as always, feel free to ask in the Slack. We need to move on to the next speaker because we're on a tight schedule. So thanks a lot, Masahito, for your very nice presentation. And Aditya, would you like to share your screen?
Yeah, sure.
All right. Our next speaker is Aditya Nema. Go ahead.
Yeah, so are my slides visible?
Yeah, you're good. Yeah, everything's good.
Okay, so good morning, everyone. I'll be talking about a measure concentration result without using any pre-shear entanglement using approximate T designs. This is joint work with Pranav Se. So decoupling is a process or a strategy by which we can transform a particular mixed state of a system AR into a tensor product state. So in particular, Dupuy has managed to show by unifying several earlier works that if you apply a Haar random unitary only to the subsystem A and then conjugate it with the input state rho AR, then send this through an arbitrary but fixed quantum channel, and then on an average, you get a state which is close to a tensor product state if certain entropic conditions are met. Furthermore, he also proved that such a result holds with high probability. In this work, we aim to do a similar thing, but by using unitaries which are less computationally hard to implement or which are efficient to implement, or in the worst, they use less number of random bits. So we resort to unitary T designs, which is a finitely supported measure that mimics Haar measure up to first T moments when the underlying function is polynomial. So one such result known in this direction is decoupling, but only in expectation by using approximate unitary T designs. In this work, we aim to obtain an exponentially high probability result, which we are referring to as the measure concentration result. So in a nutshell, our result is the following. We look at the function f, which is the decoupling function, which is the trace distance between the state that is obtained as the output of the decoupling process and the tensor product state. And omega represents the Choi-Amiolkowski state of the super operator tau. So we managed to show that the expectation of this function f, when the unitaries are coming from approximate designs, they're very similar to that of the Haar expectation, with the major difference being that we have to define two new smooth entropic quantities, which is a variant of the smooth conditionally Rényi 2 entropic quantity evaluated with respect to the Choi state. And using this, we are able to show that the function f is indeed exponentially concentrated about the mean mu. And the tail parameter of the function f is controlled by the constant or by a factor a, which is defined to be, or which is a function of the dimension of the unitary times the newly defined max smooth entropic quantity and the vanilla Rényi 2 entropic quantity. And the value of t that comes out is dependent on just this tail decay parameter a and the deviation from the mean square. Furthermore, we are able to show that these newly defined entropic quantities in the asymptotic IID limit, they are bounded appropriately by their Shannon analogs. So the challenge in proving such a theorem is, first of all, the function f is defined in terms of trace distance. So it is not a polynomial. So naively, we cannot replace a Haar random unitary by a unitary from approximate designs. So we upper bound the function f by a weighted Cauchy-Schwarz with the function g, which is defined in terms of 2 norm. So if we look at the function, which is 2 norm square, which is given by g square here, then it is a degree 2 polynomial in the entries of u. But this doesn't complete the story, as we have to do a challenging geometric analysis of the function g square so as to come up with an exponential Haar concentration result for the function g square. Then we need to define the function g appropriately by perturbing the super operator tau to tau hat in diamond norm. This is done so as to obtain the bounds in expectation and probability in terms of the smooth entropic quantities, and we have to choose the weighting operator in weighted Cauchy-Schwarz carefully so that we are able to prove the right results in the asymptotic IID regime. Okay, so our newly defined entropic quantity, which is the variant of the conditionally Rényi 2 entropic quantity, has found an application in one-shot inner bounds for quantum Mach channel, which was presented by Sayantan. He's one of my colleagues. And further, we need the concentration result to prove a process called relative thermalization in quantum thermodynamics, where we want to make an entangled state over system S and R. But since the interaction with the environment is inevitable, therefore, we have to work hard. So this is a decoupling result where the super operator or the quantum channel is just the partial trace out of the environment, and the unitary is obtained over the subsystem omega, which is a subsystem of S tensor E. So we are able to show the exponential Haar concentration. We are able to show the exponential concentration with respect to poly mod S times log mod omega designs. So our result, it saves on the number of random bits than the previous works, but our concentration is weaker than the Haar concentration, but stronger than the concentration that is obtained by appealing to unitaries which are diagonal in poly X and Z basis, answering the question that, or strengthening the belief that indeed nature does something computationally efficient. Thank you. And I would like to invite you to my extended talk for further details.
Thank you very much, Aditya, for your nice talk. So our next speaker is Nelly. Would you like to share your screen? So thanks again, Aditya.
Yes.
Hi, Nelly. Good to see you.
Good to see you, Philip. And good to see
Right.
everyone.
Yeah. Our next speaker is Nelly Ng. Go ahead, take it away.
Okay. Hi, everyone. It's a great pleasure to be part of Beyond IID this year. So this is joint work with these awesome gentlemen, Carlo, Marcel, Paul, and Jens. And it is a talk about many-body localized systems. So we start with the question of, why is a talk like this? What is it doing at Beyond IID? So the answer I think that I give is that we believe that tools within this community have large potential to find their applications in many-body physics. So in this talk, I will just try to motivate the problem and give a quick sketch of our work. So let's start. In many-body physics, one of the crucial questions is actually about how stable the observed many-body phenomenon is, especially when we start off from extremely small systems and slowly scale up in size. And this question exists even on the most fundamental level of just asking whether systems equilibrate or thermalize. So for example, consider the problem of many-body localization, or known as MBL. Here, we usually have a recipe of designing Hamiltonians so that even the local reduced states, of small size, don't even seem to thermalize, even when you have very strong interaction between different lattice sites. But actually in the field, it's not known rigorously whether it's possible for thermalization to occur eventually, let's say when you scale the system up in size or when you have much longer time scales. So in fact, there are seemingly conflicting statements about this in the literature, given that the majority of these works are in this regard are also numerical. So we decided to take the unorthodox approach, which is tools from quantum information. And in this work, we start by defining, constructing a generic thermalization model. It describes basically a reduced state within an MBL chain undergoing an energy exchange with an external bath. So this is pretty generic, and it's also very similar to that of resource theoretic thermodynamics. And this approach kind of gives us the advantage of being able to make statements about bath size. So in contrast to most studies, which can only assume an infinite dimensional bath. So we are then interested in the required bath size to thermalize the reduced state approximately in terms of trace distance. So the results, the first result is an upper bound, which depends on the max relative entropy of the reduced state with respect to its thermal version. And here the nice thing is that we can make use of the convex split lemma, which is a technical tool developed initially in the context of quantum communication protocols. And we show that this can actually be used in a thermalization scenario to bound the required bath size. So we also show that lower bounds can be obtained, also by using the convex split lemma, but here terms and conditions apply. And so this is actually very interesting because then they point to qualitative features of the many-body localized Hamiltonian. So it actually helps us to identify the mechanisms or the conditions that allows MBL to stay robust against external dissipation. So in summary, we make use of technical tools in quantum communication, but in a completely different context, so to give bounds on bath size required to thermalize many-body systems. So both the lower and upper bounds we derive depend on the max relative entropy, and we evaluate this for simple examples of MBL systems. And we see how it changes with respect to the number of lattice sites or just the reduced state size. And what we saw is that MBL actually can be proven to be quite robust using this tool. Of course, this comes under terms and conditions, but by understanding these terms and conditions better, we believe that this gives us some insight into when and why many-body localization occurs, which I mentioned earlier is a central question in many-body physics nowadays. So I hope you will allow me to tell you more a little bit about these approaches in a less hurried manner in the pre-recorded talk. Additionally, here's a small advertisement because I'm starting to build up my group in Singapore as well. But thanks for tuning in, and yes, thank you very much.
Thank you for your very nice talk, Nelly. So Paweł, are you you're up next. Would you like to share your screen? So thanks, Nelly.
Yes, I'm sharing the screen.
All right.
Can you see it now?
Yeah, everything is great. Our next speaker is Paweł Mazurek. Take it away. Go ahead.
Thank you very much, and hello everyone. I would like to share with you some observations about functioning of quantum heat engines that recently we have made together with my colleagues Marcin Łobejko and Michal Korzekwa. What is a quantum heat engine? Similarly to the macroscopic case, you have a working system and that operates in a cyclic manner. So at the end of every cycle, it goes back to the same state as at the beginning. And here it is it is marked by in black this D-dimensional quantum system. Then, of course, you have also the hot reservoir marked in red and cold reservoir marked in blue. And also you have an ancillary system that is added here in order to define work. So we will be defining work done by an engine by looking how the average energy of the battery changes during the evolution of the working body during the cycle. And for this setting, of course, there are many models of the battery, but I cannot go into details here. So some crucial questions can be asked, general questions for this kind of models. Firstly, during the functioning of the engine, some correlations can be formed between the working body and the battery. And a question would be how they affect the amount of work that can be extracted from the hot bath and stored at the battery. The second question is about the importance of the global interactions. So we can design the evolution of an engine as a result for some global interaction, and then it would be global unitary acting on all components of the engine, or we can do it in steps. We can make the working body interact first with the cold bath, then with the battery, then with the cold one, or other permutations of these steps. So the question is how our inability to perform global operations affects efficiency and power of quantum engine. Then also compared to the classical case, our working body now can be of reduced dimension. So the question is how this reduced dimension is important. And finally, if we need quantum resources here, if coherences are useful, and to what extent they are useful when it comes to power and efficiency of these settings. Of course, we are not the first ones to ask these questions, and partial answers in this setting or similar settings were already given. For example, the papers of Skrzypczyk and Woods with collaborators, they assumed global unitaries and explicit battery is our case. And one of their conclusions is that you can actually achieve the efficiency, the classical efficiency of Carnot bound. And the same bound is achievable when you do not have global operations, just the step operations, but the battery is implicit. So then the dimensionality of the working body is not tracked properly. So we want to complement this research that already have been done by designing a new model and checking its properties. And our model is this minimal coupling quantum heat engine model, and it is a step operation model with a qubit and explicit battery. And our conclusions are that the correlations that develop between the working system and the battery are important. They are tractable by looking at the ergotropy of some object that we call control marginal state that takes into account these correlations. Also, when you have a limited dimension of the working body and step operations, the efficiency cannot even reach the Carnot bound. The same conclusion applies to the limited dimensionality of the working body alone. That is visible when you compare the functioning of the engine with the Otto scheme. And finally, we conclude that coherences are not necessary. So optimal protocol, we design optimal protocol, and the optimal protocol does not rely on the coherences. But when they are classical correlations developed, between the working body and the battery, they limit the growth of entropy on the battery, and this can be useful when in future you want to extract work from the battery. Thank you very much.
Thank you very much, Paweł. So thanks a lot. Our next speaker is Kamil. Would you like to share your screen? Thanks again, Paweł.
Of course. I think, yep. Okay, can you see my screen?
Wonderful. Yeah, our next speaker is Kamil Korzekwa. Go ahead.
Thank you very much. It's a great pleasure to be here at Stanford, even though it's just a virtual presence. Today, I would like to tell you about our results in concerning encoding classical information in quantum resources. Just a second. So these are my collaborators, and the reference to the paper that this talk is based on is in the top right corner. So you're all familiar with the traditional communication scenario, and we have two parties, Alice and Bob. And Alice wants to send one of the set of M messages to Bob by encoding it in a quantum system, in a quantum state rho M, each message M in the quantum system state rho M, and sends it through a noisy channel, and then Bob has to decode it. And we look at this traditional communication scenario in the following way, that the sender is all-powerful, so she can perform all encodings that she wants, and Bob is all-powerful. He can perform all the decodings he wants, but there is no control over the channel. So this is the standard communication scheme. And then we are considering a modification of this one, called the constrained communication scenario, where for simplicity, we assume that there is no noise, so there's a noiseless channel connecting Alice and Bob, but Alice can't perform all encodings. She's constrained. So we consider a scenario where she's given an information carrier, a resource state rho, and she can only perform a subset of restricted quantum channels on it to encode information. So we have the situation where the sender is constrained, there's a perfect control over the channel, and the receiver is all powerful. And we want to analyze the communication scenario in this situation. So what constraints do we study? What kind of constraints? So mathematically, they are encoded by those two equations here, where the encoding channels EM has to satisfy these two equations for some fixed idempotent channel. You can choose any one you like. And for example, this is you can choose the G-twirling channel over some, average over some unitary subgroup, unitary group of channels. And then physically, how we interpret is that we have a system, and the system has some degrees of freedom that we want to encode our information in. And then this idempotent channel D is a resource destroying map. It erases some degrees of freedom, some information. And the encodings that we allow, that we study, are exactly those that encode information in those degrees of freedom that are removed by this resource destroying map D, this fixed idempotent channel. So for example, if you choose this fixed idempotent channel to be the dephasing map that kills all the coherences, then the restrictions that we study is just encoding classical information into those phase degrees of freedom of the system. And our results are as follows. We get the single shot upper bound for the number of messages when the average decoding error is given by epsilon, when we are given the resource state rho, and is bounded by the hypothesis testing relative entropy between a state and the state with the erased resource. And then we also, for the particular choice of the channel, this resource destroying map to be the G-twirling channel, we get single shot lower and upper bounds, and they are matching in the sense that in the asymptotic limit, they give the same rate. So we actually obtain the optimal asymptotic communication rate in this scenario, which gives a nice operational meaning for the for the relative entropy of asymmetry and the corresponding relative entropy variance. So it nicely connects communication scenarios with resource theories, and our results can be applied in a bunch of scenarios. For example, when we are restricted with encodings into purity, so when, let's say, Alice can only do mixed unitary channels, or where we can also study the super dense coding in this scenario, and some thermodynamic schemes, and also the private communication with Shepherd reference frames. So there's a range of applications that the single result can be applied to. And that's all. Thank you.
Thank you very much, Kamil. That was a very nice talk. Michal Studzinski, you're up next.
Yes.
Right. Would you like to share your screen?
Okay.
All right.
So I can start, right?
Yeah. Also, our next speaker is Michal Studzinski. So go ahead, take it away.
Okay. Hello, everyone. Thanks for coming. So today I'm going to tell you a few words about new port-based teleportation schemes. And this is a joint work with my Polish collaborators, Piotr Kopszak, Michał Chodecki, and Marek Muzrzymas. To understand our results, first we need to understand what is the port teleportation. So in the vanilla scheme, we have two parties, Alice and Bob, and basically Alice wishes to send an unknown state, theta c, to Bob. To do so, parties share and maximally entangled state called ports. And next step, Alice performs joint measurement on her half of the EPR pairs and the state which she wishes to teleport, obtaining some classical outcome I, which is transmitted through classical channel to Bob. And what is the interesting property here, that Bob, to recover the state, he needs just to pick up right port, which is described by this classical value I sent by Alice. And we can distinguish two port-based teleportation schemes. One is deterministic scheme, when the state always goes through the channel, but imperfect. And to learn about its efficiency, we need to compute entanglement fidelity of the whole process. And the second scheme is a probabilistic scheme, where the process is perfect, but we have to accept some non-zero probability of failure. And in both cases, we can show that entanglement fidelity and probability of success is a function of local dimension D and number of shared EPR pairs. And it turns out that this protocol has found a lot of potential applications. For example, it can be treated as a model of universal programmable quantum processor. We can compute some bounds on limits of quantum channel discriminations. And also it can be interpreted as a universal simulator for quantum channels. But what if parties would like to share one composite quantum state or several quantum systems? Of course, one could use standard port-based teleportation with just big dimension of the single port. But then we have to pay the price, because probably the fidelity or probability of success will be substantially lower. We propose a novel teleportation protocol where we a little bit relax our constraints on the possible correction on the Bob side, because namely here we assume that Bob is allowed to permute his ports. So then basically now Alice has to perform again some joint measurement on the state to be teleported and this half of the maximally entangled pairs, obtaining some numbers from A1 to AK, and basically these indices tell Bob on which ports he should look for teleported states. And it turns out that using symmetries in the system, for example, covariance with respect to this coset, when n is the total number of particles on Alice's side, k is number of systems to be teleported, and invariance with respect to this almost diagonal action of unitary constraints, and exploiting some SDP methods, we are able to compute exact entanglement fidelity, probability of success on the whole process, and also we are able to show optimal measurements. And relaxing these constraints on the correction on the Bob side, we see that we can really improve, for example, the entanglement fidelity a lot, because here you can see the fidelity in our protocol, this blue solid line, and for example, this blue line with this open red circles is standard port-based teleportation procedure. So allowing Bob only for permuting his ports, we can really
I'm sorry, we're running a little short on time. Could you just like conclude in 1 or 2 sentences?
So that's my conclusion, right? But basically, relaxing constraints on the correction on the Bob size, we are able to cook up much more effective port-based teleportation schemes. This is my last slide.
Thank you very much, Michal, and I'm really sorry for cutting you off. I was
no problems, I understand.
I was told to stick to my Swiss origins in terms of timekeeping. So, so thanks again for your nice talk.
Thanks.
Our next speaker is Michal. Would you like to share your screen?
Yes. Can you hear me?
Sound is good, yeah.
Okay, so I'm sharing my screen.
Okay, I'm gonna go to full screen.
Yeah.
Wonderful. All right, our next speaker is Michal Jabbour. Go ahead, take it away.
Okay, so thank you, Philip. So I'm going to present very briefly a work which was done in collaboration with Nilanjana and Data, and which concerns the derivation of a tight uniform continuity bound for the so-called Arimoto-Reni conditional entropy. So what is this entropy I just mentioned? So you obviously all know about the Shannon entropy, the Reni entropy, and you obviously all know how to extend the notion of Shannon entropy to the conditional case, as shown here. And the question is, can we do the same for the Reni entropy? And of course, the answer is yes, but there are actually several definitions which are in the literature, and we actually are interested in a definition which satisfies two properties which we think should be satisfied by proper conditional entropy, which are basically the fact that conditioning should not increase the entropy, and the chain rule. As it happens, there's one nice definition which was introduced by Arimoto, which I call the Arimoto-Reni conditional entropy, which satisfies both these properties. And so other than that, it also has like an interesting operational interest. So this is related to a talk which was given by Vishal Kataria yesterday in one of the lightning talks, in which he introduced the concept of guesswork with site information. So let me just remind you what this is. So we have what is the scheme? We have Alice and Bob, which share two random variables. Alice holds X, Bob holds Y, and he knows the distribution of X, Y, and then his task is to guess the value of X by asking a very specific question, which is big X equal to this value of X? And so what's the guesswork with site information, which was introduced by Vishal? It is actually the minimum number of questions needed by Bob to ask on average before he guesses the correct answer. And as it happens, there's a nice inequality satisfied by the guesswork with site information here, which involves actually on both sides this particular Arimoto-Reni conditional entropy for the value alpha equal to 1/2. So what is our result? So basically, we prove a tight uniform continuity bound for this conditional entropy. So we take alpha between 0 and 1, and we specify some value of epsilon, which depends on the dimension of X, the first alphabet. And we take two distributions, P and Q. And if these two distributions are close in terms of total variation distance, then we prove that they are also close in Arimoto-Reni conditional entropy, and they basically satisfy this continuity bound here, which depends only on alpha, epsilon, and the dimension of X. And so this is actually a tight bound in the sense that we can actually find two distributions which reach this bound. And let me just say that we actually also extend this to the classical quantum systems in which we have a quantum system which is with conditional on classical states. Let me just very briefly point out to one of the proof ingredients, which is this X majorization here. What it really means is if you represent your joint distribution as a matrix, it just means that for each conditional probability distributions, which are represented by the columns, you have a majorization for all of them. And we basically show that we have a notion of marginally short concave function, which really means that if we have this majorization relation for the two distribution, it implies this type of inequality for the conditional entropy. And that's all I wanted to say. So thank you. I will be uploading very soon an extended talk of this. Thanks again.
Thank you very much, Michael. And again, I take the opportunity to remind everyone, if you have questions, please do feel free to use the Slack channel to ask them. So thanks again, Michael, and let's move on to our next speaker. Angela, would you like to share your screen?
Yes. Can you hear me?
Wonderful. Our next speaker is Angela Capel. Go ahead, take it away.
Great, thank you. So I'm going to talk today about some joint work in collaboration with Andreas Blum from the University of Copenhagen. And our work is entitled A Strengthened Data Processing Inequality for the Vilasini-Stachevsky Relative Entropy. One way to generalize the classical relative entropy between measures is the frequently used omega k relative entropy, but here we focus on another possibility, which is called the Vilasini-Stachevsky relative entropy, and it's given by this expression that I write here. And if sigma and rho commute, we can see that both expressions reduce to the same quantity, but in general, since they don't, the BS entropy is always written on equal to the relative entropy. So the motivation and starting point of our project is the perfectly well-known property of the data processing inequality for the relative entropy for quantum channels, and the conditions for equality that were early studied by PETs, which essentially say that there's equality in the data processing inequality if and only if one state can be recovered in terms of the other by means of a recovery map, and in particular, this recovery map can be chosen to be the PET's recovery map. When we consider now the difference between the relative entropy before and after the application of the quantum channel, of course, we know that this is always greater or equal to 0, but now we want to strengthen the right-hand side of this inequality. And we consider the possibility of trying to do that in terms of the PET recovery map applied to one of the states. So can this be done? And in particular, can this be done in terms of the relative entropy between a state and its PET recovery? And the answer is that this is not possible, and this was done by Brandau et al. In 2015 and Fassi in 2017, and it was shown numerically in this case. But if we consider another different distance measure, such as, for example, the one norm of the difference between the two quantities, then in this work of Kalden and Berginina of 2017, they showed that for conditional expectations, this is the case. So the difference between these two quantities can be lower bounded by this one norm of the difference between the two states and some multiplicative factors. And they subsequently lifted these results to standard divergences. So this is the starting point for a project, since now we consider the analogous question in the case of the DPI for the BS entropy, since we know that the DPI holds for the BS entropy. And then we want to provide a lower bound for the DPI in terms of some possible BS recovery condition. So before we need to provide this BS recovery condition as an analog for the PET's recovery map. And this is what we have done in this project. So first, we proved in general for any quantum channel that there's equality in the DPI for the BS entropy if and only if one state can be recovered in terms of the other by means of this expression here. And this expression in particular, we called it the BS recovery condition. And moreover, we used this BS recovery condition to provide an analog of the result of Kalden and Berginina, but now for the difference between the BS entropy before and after the application of the quantum channel. So here you see that the quantity that we obtain is essentially analogous to the difference between the state and the PET recovery map, but now for the BS recovery condition, which, just to clarify, has a bigger set of fixed points than the PET recovery map. So just to conclude, let me compare both results. So for the relative entropy, we have the PET recovery map, and in our case, we have the BS recovery condition, which is like an asymmetric version of the latter. And you see how the two results of Kalden and Berginina and ours compare. And in our case, we also managed to extend this to maximal divergences as they did for standard divergences. So for further information, please go to my extended talk, and thank you very much for your attention.
Thank you very much for your very nice talk, Angela. All right. So Vilasini, you're up next, right?
Yes. Hi.
All right, perfect. So thanks again, Angela, and Vilasini, if you can share your screen.
Yes. Can you see my screen?
All right, wonderful.
Yes.
So is everything okay?
Yes, all is good.
Wonderful. So our next speaker is Vilasini and looking forward to your talk. Go ahead.
Okay, thanks a lot, Philip. I'm glad to be here. I will be talking about this joint work with Christopher Portman and Lydia Del Rio, who are both my collaborators from ETH Zurich. And the talk is about composable security in relativistic quantum cryptography. And it's based on this paper that we put out last year in New Journal of Physics. Okay, so firstly, I wrote 3 haikus to summarize what this paper is about. Firstly, what we talk about is cryptography. And in cryptography, what we typically want is not just the security of a single protocol or a resource, but we also want resources and protocols to remain secure when they're used as subroutines inside other protocols and resources, right? For example, the resource R here, we would want it to remain secure even when it's used in such a protocol to construct another resource S. Secondly, we want to consider a general class of scenarios where not only agents are exchanging quantum systems, but they can also be distributed over space-time. And in this case, we also need to take into account the speed of signaling between these agents. For example, if you see the space-time diagram here, some agent at A can signal to an agent at B, but not to an agent at C because they're space-like separated. So you need to consider both quantum as well as relativistic constraints here. And what we note is that there is no model for talking about composable security of these general class of protocols. So we propose such a framework here. And we also prove some new possibility and impossibility results. For example, that given some cryptographic resource, you can construct some other resource, or given some resource, you cannot possibly, using any protocol, construct another resource as shown here. So that's the overview. So what do we already know? So I will talk about, in particular, bit commitment, because it's an important cryptographic primitive. And basically what a bit commitment protocol tries to achieve is the following. So we have 2 parties, Alice and Bob. And Alice wants to commit a classical bit A with Bob. So she inputs this bit A to the ideal resource. And the resource tells Bob that Alice has committed to a bit. And then at the next stage, at some later time, Alice can decide to open her commitment to Bob. And then the resource will give Bob Alice's output, the initial bit A. The important thing is that Alice cannot change her commitment after she has committed, and Bob does not know the value of A before Alice opens it. And this is nice because given composably secure bit commitment, you can construct all these really nice cryptographic primitives. What is known is that using non-relativistic quantum protocols, you cannot have secure bit commitment, either in a composable manner or using just a standalone security. And what is also known is that using relativistic quantum protocols, you can have bit commitment that has standalone security. But these protocols are not composably secure. For example, if I use this protocol to construct a bit commitment resource, and I use 2 such resources in parallel, then I can compromise the security of both of them. So they're not composable. So the question is whether composably secure bit commitment just from communication between 2 parties is possible using relativistic protocols. So firstly, to even answer this question, we need a framework, because there's no framework for talking about composable security of these very general class of protocols against classical quantum and no signaling adversaries. So we developed such a framework. And we show the following. So this is just an overview of what is already known that I mentioned before. What we do is we define a new resource called a channel with delay. And the motivation for this comes from the fact that in relativistic bit commitment, the commitment is usually timed. It depends on the time taken by light to travel between different agents. So it acts more like a channel with delay. So we define this new resource, and we show that you can, in fact, construct a coin flipping resource given this channel with delay resource. That's our first result. Then we show that given direct communication, it's impossible that there doesn't exist any protocol that will allow you to construct secure coin flipping just by direct communication between the 2 parties. And as a corollary of this result, we have also the impossibility of relativistic bit commitment and channel with delay from direct communication alone. And finally, we also ask the question of, given this channel with delay resource, suppose we're given n such resources, is it possible to construct a channel with a longer delay? And we find that this is also not possible. it to do in a composably secure manner. And I note that all these impossibility results also hold for protocols where parties send messages in a superposition of space-time trajectories. For example, Alice can be in a superposition of sending a message to Bob and to Charlie, who are at different space-time locations. So such scenarios have been looked at in the so-called quantum switch before. So this gives us a framework for analyzing the information theoretic advantages that such general processes could provide us with. So with that, I'd like to thank you for your attention. And
thank you very much, Vilasini. And I suggest we all unmute our mics and clap for everyone in the session. We had some very nice talks during the session.
I had a quick question, if you don't mind. There was the nice diagram at the end. So there's no relation between channel with delay and bit commitment or the others, or it's just unknown, or?
Yeah, thanks for the question. So yeah, that is not known actually between the channel with delay and bit commitment, because actually, as I mentioned, relativistic bit commitment in itself seems to resemble a channel with delay and more than bit commitment itself. So there's also this slight discrepancy in what people have already done.
Okay.
So I think this would be the relation that I showed of trying to extend the delay of a channel, because bit commitment in a way can be thought of as a channel with an infinite delay or arbitrary amount of delay. So I would say that's roughly the relationship.
Okay, thanks.
Yeah, thanks for the question.
Well, thanks again to all the speakers in this